Hello and welcome to another LeetCode problem. Today we're going to be doing LRU cache. And so in this problem we're trying to design a data structure that follows the constraints of a least recently used cache. And it's going to have a size, it's going to have a get and a put, where a get will get the value of a key if it exists, otherwise -1. Put will either update the value of a key or insert a key value pair. And we need to make sure that we have the right capacity. And they need to run an O1 average capacity. So what we're actually going to do for this is we're going to have a linked list for the cache, and I'm going to kind of show you, we're going to go through this example with a linked list. So what we're going to do is we're going to have a head and a tail. So actually this is going to be the head. This is going to be the tail. And we're going to be putting in nodes, and we're going to be putting in nodes at the tail and evicting them at the head. So the tail is going to be the most recently used, and then the head will be the least recently used. So let's show you what that's going to look like. So our capacity here is 2. So our capacity is 2. So first, let's go through this example. We're going to be putting in node 1, 1. So it's going to have a key 1, value 1. We're going to always put in at the tail. So we're going to say, let's have a 1 and a 1. So let's do that, right? So key equals 1, value equals 1. We're going to make a node. It's going to be a doubly linked list. So it's going to look like this. Now we're going to put in a 2. And so when we put in a 2, remember, we're always going to be inserting the tail and deleting at the head. So when we're putting in a 2, what we actually need to do is we need to actually take this and move it over here. So let me actually delete this. I'm not going to show the lines, but I will show the actual node. So hopefully this moves. Okay. So but know that these are like connected in a doubly linked list. Okay. So we have this 1 1. Now we need to put in a 2 2. So let's do that. So we need to put in ka equals 2. Value equals 2. Okay, now we access value 1, and so when you access value 1, these actually need to get swapped because now value 1 was just used, and so now every time you access something, it needs to go to the tail. And so now, well, what are we going to have? Well, we're going to have to flip these nodes essentially, right? So let's do that. So let's actually take this node. Let's take this node, move it over here maybe, and let's take this node and move it over here. Now we can put this node and we can just move it, I think. Whoops. Let's see here. Let's take it. Let's move it over here. Okay. So now that this was the case here, right? So we returned 1. Now it's the most recently used. Okay. Now we're putting in 3 3. Our capacity is full. So where are we evicting? Well, we're obviously going to have to be evicting from the front, right? We're evicting from the head. So what we're going to do is we're going to evict from the head. So this node is going to go away. And now we're going to put in a 3 3. So let's actually redraw this again. So we're going to have a head, tail. Now we're going to take this node and we're going to move it over here essentially. So we're going to take this, we're going to copy it, and we're going to put it over here. And now we put in a new node. So we're going to put in a new node over here. Then that's going to be, change the color of that. Okay, perfect. So we're going to make a new node over here, and now this is going to be the 3 3, right? So K3, value 3. Okay, now what are we doing next? We're getting a 2. So if we try to get a 2, there is no 2, so we need to return -1. Okay, now we need to put in 4 4. So what are we going to be evicting? Well, we're going to be evicting this, right? So this is going to be evicted because that was the least recently used. So we're going to be evicting that, so let's do that. Let's evict this. Now we need to put in another value, so let's actually give us some more space here. So let's actually copy some of these down here. So what we could do is we can actually copy this down here. And then we're going to be getting rid of this node. So let's get rid of this node. We're going to take this node, we're going to put it over here, and we're going to delete it from here. And now we're putting in a 4 4 essentially, right? So we're putting in a, let's change the color of that. So there we go. So we're putting in 4 4, okay? Value 4. This is value 3. Okay, so we put in a 4 4. Now we try to get a 1. We can't do it. And then we try to get a 3, and we can do it. But now that we got the 3, we need to put the 3 in the back because we just used it, right? So we need to swap these two essentially. So we're going to do that. So let's take this. Let's move it over here. Let's take this. Let's move it. Whoops. Let's take this. Let's move it over here. And then finally, let's take this and let's put it over here. And so now this is going to be our final list. So you can see how you need to do these swaps. So let's just go through every single operation and like what are the steps, right? And we're going to have some helper functions. So we're going to have 2 helper functions here. So we're going to have one helper function. It's going to be remove. And what's that going to look like? Well, let's take a look. So if we have a head and a tail, right, and some nodes, let's say we have a head and a tail, and we have some nodes. So let's just say we have node 1, node 2, node 3. Actually, it's a little bigger. Node 2, node 3. This is the head, this is the tail, this is node 1, node 2, node 3. So remove is pretty straightforward. We're actually going to store these nodes in a hash map. And the hash map is the key is going to be the key of the node. So we're going to have a hash map where the key is going to be the key of the node and the value is going to be the node itself. And so to remove a node, it's pretty straightforward. All we have to do is take the left and the right, and we have to make them point to each other, right? So if you remove this node, all you have to do is just make these two point to each other, and that node is removed. So that's how our remove is going to work. Now let's look how an insert is going to work. Insert is pretty straightforward as well. And by the way, so when we remove the node, we're also going to remove it from the hash map, right? Like we're going to have a hash map with every single node, and then when we remove, we need to remove it from the hash map. So an insert is going to work similarly, right? Like let's say we have two nodes here, and let's say we have the head and the tail again. So let's say we have the head here, we have the tail here. So inserting is pretty straightforward. All we need to do is we need to get the tail, and we need to get the node to the left of the tail, and we're just going to insert right between them, right? So insert, we're just going to insert straight into here, and we're going to put in a node here, and then we're going to add that into the hash map as well. We're going to add the node into the hash map. So these two we're going to use over and over and over for our get and put and things like that. And I'm going to show you how. So we're actually going to figure out how we're going to do this get and the put, right, to make them big O of 1. So for the get, we need to check, does the key exist? So we're going to have a hash map with every key, right? So we can just check our hash map with keys. And if the key does not exist, we can just return -1. But if the key does exist, so if you think about it, like, let me give you an example here. So let's say we take this. Actually, so let's say we take all of this and we're trying to do a get here, and our nodes are labeled 1, 2, 3, and we're trying to get this node here. So we can get it, but remember, when you do a get, then that makes it most recently used. So you not only have to do a get, you have to put it over here. So let's think about how we could do that using our helper functions. So a get is actually just a remove and then an insert. Right? It's a combination of those. If we remove and then we insert, that's a get, right? We remove this node and we put it in here. That's what we wanted. And then we return the value. So a get is just a combination of a remove and an insert. That's literally all it is. And if the key doesn't exist, we just return -1. So that's pretty straightforward with our helper functions. Now let's look for our put. What is that? So if the key does exist, then, so let's look at the cases, right? If the key does exist, so if key, then remove the value, like remove the node, essentially. Like let's go through this again, right? Let's say we have our get, or sorry, our put. So let's draw this like this. Let's just draw a head, tail, and let's draw 3 nodes. So 1, 2, 3. So this is 1, 2, 3. So let's say we're trying to get 2 here, and we're trying to update the value. Well, to update the value, you want to remove it and you want to put it here, right? Because it's still most recently used. So if it is there, we're just going to remove it, right? We're removing, and if it's not there, we don't have to do anything. Then we have to check, is our cache full? Is cache full, right? So if the cache is full, if there's too many nodes, like let's say the capacity is 3, if there's too many nodes, we have to remove a node. So if the cache is full, we remove. Where do we remove? From the front, right? Because least recently used. If the cache is full, we remove a node, and then finally we put in the node, the new node over here. So it's just a remove if the key exists, if not, do nothing. If the cache is full, remove, right? So remove from the front, pretty straightforward. And then finally put in node to the cache, or to the cache. So let's look at our stuff one more time. So we have a helper. We have a helper that will remove. We will always be removing from the front, right? Because it's the least recently used. We're always removing from the front. Yeah, we're pretty much always going to be removing from the front. And to insert, what do we have to do? You could also remove from not the front, like if you wanted to. You could technically do that, but we're usually going to be removing from the front. But regardless, the remove is going to take a node, and we're just going to take its left and its right point to each other, essentially, for the remove. So we're usually going to take the node that's at the front. Okay, and then our insert, or sorry, we have a remove, we have an insert. Insert will always insert in the back. And then finally, our get is just a remove and an insert, and our put is a remove if there is a node, if not, do nothing. If the cache is full, let's remove, and then finally put in the node. So now we have everything we need to actually write up the code, so let's do that. So we're going to first initialize the cache. So remember, we actually, before we initialize the cache, we need to, since we're using a linked list, we need to actually make a class for nodes, right? So we can just say node, and then we can just initialize it. So what does it need? What does it need? Remember, the node's going to have the key, the value, the next, and the previous. And then we just say like self.key equals key. This is just pretty straightforward constructor. Self.value equals value. Self.next equals next if it was provided. If not, make it none. Self.previous equals previous. Okay. So for the init, what do we have to do? Well, we have to make a head and a tail, and we have to make them point to each other, right? Like in the picture. So let's do that. So self.head equals new node. It's going to have a key of whatever value, 0, 0, and it's not going to point to anything. Now we need the tail. So new node, this actually needs to be node. Okay, so 0, 0. Okay, pretty straightforward, this needs to be over here. Alright, now we need to make the tail point to the head and the head point to the tail, so let's do that. So self.head.next equals self.tail, and self.tail.previous equals self.head, right? That part's pretty straightforward. Then we need to have a capacity because we're going to be checking, is our cache full or not? So we're just going to make that equal to the capacity here. And then finally, this is going to be our dictionary of where all the nodes are stored, where it's the key is going to be the key of the node and the value will be the node itself, so that way we can remove it easily. Okay, so now we need to write our helper function, so let's do that. So we're going to make a helper function of remove, and we're going to make a helper function of insert. So remove self node. Remember, we're going to be removed from the front, but essentially all we're doing is we're just making the next and the previous of the node point to each other. So we're going to say, let's take the previous of the node and let's take the next of the node and let's have them point to each other, right? So previous.next, next.previous, point to each other, and then now the node is removed. We're going to handle actually removing it from the hash map in other places, and the same thing for the insert. We're going to handle those in other places. These recursive remove and inserts are just going to handle actually inserting it into the linked list. Because sometimes we're going to want to remove something and then put it back in another spot, so we don't need to actually delete it from the hash map. So for an insert, pretty straightforward, right? We're going to use a tail in the previous node of the tail. So it's going to be previous next equals self.tail.previous and then self.tail. And we need to put it in between these two nodes, right? Self.tail previous and self.tail. We need to put it right in between those. And so it's pretty straightforward. So previous.next and self.tail.previous equals node and node. And then finally node.previous, node.next equals self.tail. Okay, so this is actually NXT. Hopefully I didn't make too many spelling mistakes, otherwise it's going to be a pain to debug. That's okay. Okay, so now in our get, remember what we're doing, if the key does not exist, we can just return -1. So if key not in self.locations, where self.locations is going to have all the keys and the nodes. So let's just return -1. And remember, if it does exist, it's just a simple remove and then an insert. So we're going to say node equals self.locations key. Let's actually get the node. Let's remove the node. Let's insert the node. So self.remove node, self.insert node to update it to the most recently used. And finally, we can return the value of the node. Okay, so that part's done. Now we need to do the put. So let's actually give us some bit more space here. So for the put, remember, if the key is in there, then we need to remove it, right? So if key in self.locations, we need to remove it. So let's get the node, key, and self.remove the node. And we're going to remove it from the hash map. And now the rest of it is going to be the same code regardless of, you know, if the node was removed or not. So we're going to remove it from the hash map here. Okay. And now what do we do next? Well, we need to check the capacity. If the capacity is too big, we need to remove from the front to give ourselves some space. So self.capacity How do we check if it's too big? Well, we can just check for the length of self locations, because self locations is going to be every single node. So let's say self capacity is 2 nodes and the length of this is 2 nodes. That means our cache is full. So if our cache is full, we need to be removing from the front, right? So that's pretty straightforward. So what do we need to do here? Well, we need to be removing from the front. So we can call like node to remove. What node are we removing? Well, we're removing the node right after the head, right? So we're going to do self.head.next. So actually, just a small little error that I was talking about. So when we remove, we're not always removing from the front, because when we do these gets, we're actually removing from the middle, right? Like if you get a node from the middle of the list, when you're appending it to the end of the list, you're actually removing from the middle. So that's why our remove doesn't necessarily remove from the front. This remove works for anywhere. But now we are going to be removing from the front in this case. So that's just a small thing there. Okay. And now so self.remove, we're going to be removing the node to remove, right? To remove. Okay, and now we need to actually pop it from the dictionary because it no longer exists. So pop. I think you can use delete as well. It's totally fine. Node to remove dot key. So whatever the key of that is, we're going to get rid of that in the dictionary, and we're going to get rid of the entire node. Now we need to create a new node, regardless of if we had to pop or not, regardless of these two conditions. So we're going to say node equals node key value, and now our node is going to be good to insert because we checked if our cache was full already, so now our cache is guaranteed to not be full. So now we can put it into the dictionary. So node.key equals node, and then we finally need to insert it, right? So self.insert. Okay, and we have one final step, and that's to pray that I didn't make any errors, which I probably did. So we'll see how that goes. Yeah, definitely not the smartest idea to be doing a linked list problem without having code done like earlier, but we'll hope for the best. Nice. Okay. All right. So now let's go and let's just check all our functions to make sure they're big O of 1, right? So this remove is pretty straightforward. We're just changing 2 pointers. That's obviously big O of 1. Here, same thing. We're changing a couple pointers. Obviously big O of 1. Here, if the node is not there, that's big O of 1. And then we're doing remove, which is big O of 1, and we're doing insert, which is big O of 1. So that's the key. We're reusing these functions, and both of these are big O of 1. And we're just getting it right away, and we're removing. We saved a step by using hash map. We no longer have to iterate through the entire linked list, which would be big O of n. So if you want a linked list, but you need to get the items right away, the way to do it would be a hash map and put the linked list in them. So you could also design a linked list like this, where you could put the nodes in a hash map, and then that would help you to get quicker deletions and insertions. That would give you O1s, deletions, and insertions at the cost of using more space for the hash map. So it's a trade-off there. Okay, now so this get, like I said, is big O of 1 because we're just doing a remove and an insert. And now here we're also doing a remove, big O of 1, a remove, big O of 1, and an insert, big O of 1. And so all of these are big O of 1. And for our space is obviously going to be like whatever total nodes we have, you know, so like big O of n, however many total nodes we're actually storing in the list. So we're essentially going to have them here, and then we're also going to have the hash map point to them. So yeah, it's going to be big O of n. All right, so that's going to be it for this problem, actually. Hopefully you liked it, and if you did, please like the video and subscribe to the channel. And I will see you in the next one. Thanks for watching.